In the last lecture, we had been talking about static timing analysis. So, if you recall, in STA what we are doing, given a combination circuit netlist typically at the level of gates, we were calculating for every interesting points of the circuit something called actual arrival times, required arrival times and their difference, that is the slack. So, by looking at the slack, we can tell which of the nets or which of the segments of the netlist are critical, in the sense that some of the slacks may become negative. Now, if a slack becomes negative, then during a subsequent step we have to adjust the delays and some sizing of the gates or wires or inserting buffers, so that slacks can be made positive. Now, there is another thing to be considered as well. Suppose we find that our static timing analysis is not giving any timing violations, but what we find is that in many of the lines we have a very high positive slack value. What does a positive slack value mean? It means our required arrival time is larger than the actual arrival time. Suppose we find that it is significantly larger. So, why would you want that? We would not like to have that, because we want to have a circuit that is running as fast as possible. So, if I unnecessarily give a very large positive slack, that means I am trying to run the circuit at a slower speed. So, even if this signal has arrived, means my requirement is this, I am unnecessarily making the signal arrive earlier. Okay. So, I can introduce some delays, I can make some gates smaller, I can do some other kind of optimizations, so as to make the slacks as close to 0 as possible. That is one of the optimization criteria in this step, right. So, I do not want to, you can say, compromise on the quality of the timing, but I can reduce the complexity of my design by introducing delays in some places. By introducing delays, I can make some of the positive slacks close to 0, and if it is close to 0, then I am happy with my design, that I am trying to do some kind of optimization with respect to the resources that are available to me. So, in this lecture we shall be actually talking about one kind of an extension to the static timing analysis, that is a very well known algorithm called the zero slack algorithm. So, a process by which we try to make the slacks 0 in all the lines. So, let us look into it. So, we use a concept called delay budgeting, which means at the output of each gate we are putting some delay budget. That means how much additional delay we require there. Okay. So, once we have the delay budgeting, at a subsequent step we can do some physical process by which you can actually increase the delays in those lines by some means. Delay budgeting means at the output of some gates we can specify that, well, I need 2 additional units of delay here, I need 3 additional units of delay here, and so on. Delay budgeting concerns that some delay values I dynamically calculated in an iterative way, and at the end it will give me by how much units I have to increase the delay in certain lines. Okay. Okay. So, there are a few interesting points here. First is that in timing driven design we are typically considering both the wire and gate delays, right. So, we are trying to optimize them, but there exists a dilemma, which one has to be done first. Like for example, so when we do timing optimization, so we are considering weights of the wires, okay, we are considering wire delays, which means that we have good knowledge of capacitive loads, we have good knowledge about the actual wire delays, because unless we have knowledge about the capacitive loads, so our estimates of the wire delays can be quite inaccurate, right. This is the point to note. And the second point is that unless placement and routing are completed, we do not know the wire lengths. So, unless we know the wire lengths, we do not know the capacitive loads. So means unless we do the timing optimization, we cannot do placement and routing in an optimum way. So, there is a dilemma, which one of the two to do first. Shall we do placement and routing that are timing aware first, or shall we do the timing optimization first? So, because of this dilemma, typically this process are integrated as much as possible. They are done, means almost at the same time, hand to hand. Okay. So, in the zero slack algorithm, we are using the concept of a time budget. So, what is a time budget? For every net, we are establishing some delay constraints in terms of the wire length, in terms of the gate delays. These time budgets can later on be used for fine tuning placement and routing, so that these delays and wire length constraints can be met. Okay. So, we shall see, we shall illustrate it through an example also, that how it works. Let us look into it. First, let us introduce some notations. So, we consider a netlist consists of a number of gates. Let us call the gates as V1, V2 to Vn. Then we consider a set of nets. Like, what is a net? Suppose the output of a gate goes to the input of 3 gates, let us say. Suppose this gate is Vi, then this interconnection, this output is going to 3 places. This is a single net. This net I am calling it as Ei. So, Ei is the net corresponding to the output of gate Vi, right. So, we consider a set of such nets which indicate interconnections, where Ei is the output net of gate V, and Tv and Te will denote the gate delay and wire delay respectively. So, here for example, in this example, when I say T of Vi, it means the delay of this gate, and when I say T of Ei, it will consider the delay of this whole net, the output of this gate going to the inputs of these gates. So, the worst case delays of this entire net, right. So, we have two parameters, Tvi plus Tei. So, when we say that some signal is coming to the input of Vi and it is reaching the input of the next gates, so the total time will be Tvi plus Tei, right. Okay. So, these are the notations. The zero slack algorithm, what it does, it takes the netlist as input, and as I said, well, here I am assuming one thing, that there are no negative slacks. If there are negative slacks, I have already made some adjustments, so that the slacks have become all positive, okay, that I am assuming. So, once I have a netlist with the slack values calculated and the slacks are positive, we start from that point. So, we try to decrease the positive slacks and try to make them 0. So, how we are trying to decrease the positive slacks? So, we can decrease the slack. Slack is what? Required arrival time minus actual arrival time. So, how I can reduce the slack? You see, just to recall, slack is defined as required arrival time minus actual arrival time. Suppose slack is a value which is greater than 0, positive, which means RAT is greater than AAT. So, how I can make it 0? I can make it 0 by increasing AAT. So, how I can make this AAT increase? So, I can either increase the delays of the gates like TVI, or I can increase the delays of the nets TEI. So, delays of the gates I can do by scaling down of the gates, making them smaller. So, increase of the interconnection delay I can make by appropriate routing. So, instead of a straight routing, maybe I can make a zigzag kind of a route and then route like this. Okay. So, roughly the idea is this. Fine. So, including TV and TE, so what we are doing is that we are trying to decrease the slacks to 0 by increasing TV and TE that constitutes the timing budget. So, the timing budget for a node or a vertex V is defined as the delay of that particular gate plus the delay of the output net. So, this corresponds to the total timing budget of that node. So, once the timing budgets are calculated and the slacks have been reduced to 0, your objective will be to try and achieve this timing budget by appropriately adjusting the physical parameters of your layout, okay, either making the gate smaller, making the wires longer and so on, making the wires thinner. There are so many ways. So, here as I said, if TV is exceeded, so you have to make it smaller, then you can decrease the wire length, you can increase the size of the gate, but if it is the other way around, you will have to do the reverse. Now, the delay impact is often estimated using the Elmore delay model, because it gives a quite accurate estimate, provided you have made a relatively accurate estimate of the capacitive and the resistive means effects of the neighborhood, the other lines. Okay. So, once you have had a fair estimate of the resistance and capacitance, we shall be talking about this later, how we can make these estimates. Then you can use the Elmore delay model to make a fair estimate of the delay, how we can make that calculation, right. Okay. So, the point is that if we find that in a timing path, if most of the edges are within the timing budget, then it is possible that the path can meet the timing constraint, the entire path, even if some arcs cross their timing budget. So, there is a process called rebudgeting, means it is an iterative process where the time budgets are calculated and modified in an iterative way. So, at the end you get the final values which you have to meet at the end, right. This is sometimes called rebudgeting. So, we shall be explaining the zero slack algorithm with the help of an example. Let us see. First, the basic steps. See, so you have to clearly understand the steps, because otherwise it will be difficult for you to understand the steps. You see, first step is the conventional static timing analysis. Given the netlist, you calculate AAT, RAT and the slack values. So, you determine the slack values of all the nodes, you select a node, let us call it V min, which has the smallest positive slack min. Well, here I am assuming that the slack values are all positive, because if a slack value is negative, I am not touching that, because negative slack values can be handled post this timing analysis by using some geometric modification to the layout. Okay. Well, so once we have found out a vertex V min with the minimum positive slack, then you find out a path. Like for example, you have a netlist, you have found out a vertex called V min. Then your next step will be to find out a path through some other vertices, let us say V1, let us say V2, let us say V3, let us say this is the path, this is the whole path, such a way that this particular node is having the minimum slack. So, I call it as slack min. What I am saying is that this path is dominating the value of slack min. What is the meaning of this dominating? Means if we make any changes in the delays here or here or here, either in the delay of the nets or the vertices, then slack min will also change. This means dominating. Okay. So, if I can find a path in the circuit such that this property is true, then you consider that path together at a time. So, the second step says you find such a path. That means, any change in the delays in vertices along the path will also cause the slack mean to change. Okay. Now, suppose in this case, this step is important, let us understand. Suppose you find that in this vertex your slack was, let us say, slack value was 6 plus 6, let us say slack value was, let us say, 5. So, the third step says, so you have to make the slack value 0 somehow. So, this slack value of 5 you try to distribute among these vertices along the path. So, there is V1, V2 and V3. Let us say you add plus 2 here, you add plus 2 here, you add plus 1 here. So, the slack value of 5 you distribute evenly across the slack value, so that what was 5 here, now this becomes 0, right. This is the basic idea. You are trying to divide or distribute the slack value across all vertices in the path. Your objective is to make this slack mean equal to 0, right. Fine. So, this is this third step. So, each budget increment, whatever you do, will decrement the slack value of a vertex. So, if you increase the delay of a vertex, like for example, here V1. So, you are increasing the delay budget by 2. What does that mean? You are increasing the actual arrival time by 2. If you increase actual arrival time by 2, means you are also decreasing slack by 2, slack equal to RAT minus AAT. Okay. So, increasing the time budget of a node will also cause a decrease in the slack value. So, slack values will all go towards the downward side, from a higher positive value to a lower values. Okay. Fine. So, this is what is mentioned, each budget increment will decrement the slack value of a vertex. So, you go on repeating the process. After making this change, again you recalculate this slack values, and you again find out the minimum slack node, again find out a path, again distribute, go on repeating this. At the end you will be finding that all the slack values have been reduced to 0. This is the basic objective of the zero slack algorithm. So, let us just illustrate this with the help of an example, so the process will become clear. So, at the end whatever you get, that is the output of ZSA. Let us take an example like this. There are 5 gates. So, let us understand the notations first. There are 4 normal gates. Well, I am showing it as AND gates, but it does not matter, any kind of gates, and this is a buffer, let us say, and the values which are shown inside the gates, they indicate the gate delays. So, by properly sizing the gates, I can adjust the gate delays, this you already know, right. So, let us just work this out, because it will be easier for you to understand. Let us just work out this circuit here. Suppose I have a gate like this, output of this is going to another gate, this has a delay of 4, there is another gate, delay of 3, there is another gate 6, this is the output, buffer, delay of 0. So, this is your circuit, initial circuit. So, let us assume that your actual arrival time, I am calculating AAT, let us denote it as A. So, AAT of this node is 1, So I am directly calculating, I am not showing that S node, S is implied, okay, I am just showing it. This A is 1 and this A is 3. Let us say the inputs are arriving at these time steps, and just initially we assume that all delay budgets are equal to 0, there is no delay. So if you calculate the AAT value, so this delays of the wires are assumed to be 0 initially, okay. So the value of A here will be 1 plus 2, this A will be 3, here it will be 3 plus 4, A equal to 7, here it will be 1 plus 3 and 3 plus 3, whichever is larger, 6, 6 and 7, whichever is larger, plus 6, 13, 7 plus 6 and 6 plus 0, 6. These are the arrival times, right. Similarly, if you calculate the required arrival time, suppose the required arrival time for this node was specified as 17, for this node it was specified as 14, let us say. So again you do a back trace for this. So if you go back here, it will be 17 minus 6, it will be 11. If you come here, there are two paths, 17 minus 6 coming here and 14 minus 0 coming here. So it will be 11, that will be shorter, minimum R equal to 11. So you come back here, 11 minus 3, it will be 8. Similarly 11 minus 4 or 11 minus 3, whichever is smaller, 7 is smaller, so it will be 7, and here R equal to 11, it comes here, so it will be 11 minus 4, 7, 7 minus 2, it will be 5. So you see, once you have calculated the actual arrival time and the required arrival time, you can also calculate the slack, RAT minus SAT. What will be the slack? Here S will be 5, here S will be 6, 7 minus 1, S will be 5, S will be 4, S will be 4, S will be 4, S will be 5, S will be 8, and here S will be 4. Okay. Now we are actually representing these three values in the form of a tuple, where you show the actual arrival time first, then the slack, then the required arrival time. This is the notation we use, and within bracket we are showing the timing budget. That timing budget actually will indicate the delay of the gate plus delay of the output net. So we are considering them together. Okay. Suppose I find that for some node TB has been calculated as 5, so my gate delay plus the net delay total has to be 5. Okay. That way I will have to adjust it. Now this is the notational convention, right. So these, with these initial values as I have calculated, so this diagram actually shows that exactly. So whatever I have calculated, these are the 5 values, AAT, slack, RAT, 145055. So exactly what I have calculated, and the timing budget initially is assumed to be all zeros. So this output O1 and O2 I am showing it separately. Okay. Now let us move step by step. The first step says you identify the node with the minimum positive slack. So you see here that the minimum positive slack is 4, it is 4 here, 4 here, 4 here, 4 here. So you pick up any of the nodes, this entire path will be a dominating path. So the path marked red, that will be the minimum non-zero slack. So now what you do, as I said, let us say you pick up this, you make this 0 4 and distribute this slack of 4 among the different paths. So this 4, whatever was there, this was 4, this 4 you distribute as 1, 1, 1 and 1. That means along the wires you distribute. So, if you do it, the delay, the slack that was 4, that will get decremented by 4, because now the entire path delay has increased by 4 units. So, the slack will be reduced by 4 units. Okay. This is the first step. So, you see earlier it was 145, if you decrease the slack to 0, this RAT will also become 1, because RAT minus AAT is slack, right. This is the first step, and this is 1. So, at O1 it will be 16 plus 1, it will become 17 with this delay. Okay. You repeat the same process. Next step, you find this 2 is the smallest positive slack, and it does not, no other node is dominating this, only this one. So, just reduce it to 0, increase the slack here, reduce it to 0, increase the time budget here. Okay. Make this while longer, making 0. So, this has become 0. Repeat this process. Now, you see 4 is the smallest. So, let us choose this path, 4 and 4. So, this delay of 4 you can distribute similarly. Let us say distribute as 2 and 2. So, it was 1 4 5, it becomes 1 2, 6 4 10 becomes 6 2. So, this 2 and this 2, the RAT also gets decreased by 2 each, 5 and 10 becomes 3 and 8, right. So, same process you repeat. Now, you have again, you see it has not become 0, again this is 2 is the minimum. So, again choose the same path. So, again distribute this 2 across 1 1, this becomes 3, this becomes 3, and now this 2 will become 0, this 2 will also become 0. So, this has become 0, this will become 0. Now, the non-zero ones are this and this. Now, you can choose these two in 2 separate steps, but I am showing in one step. This is one path, this is another path. So, to make this 0, you have to increase the budget here. To make this 0, you have to increase the budget here, because it was 10 4 14. To make it 0, to make this TB as 4. So, at the end you see you have obtained a time budget values that will indicate what will be the delay of these different wires, so that 0 slack can be achieved in all lines. So, 1 4 1 3 1 1 2 3 1, these are some guidelines for your next step of routing, let us say, where you can actually route your wires such that, or size the gates such that these delay values are actually achieved, right. So, you can have one small modification to this ZSA algorithm. You see, ZSA actually uses late mode analysis. That means, we are looking at the worst case delays, that means we are looking at only the setup constraints, the latest time of signal transitions, but we are also interested to look at the hold time constraints. Okay. There is a modification to the ZSA algorithm called early mode analysis, where we look at the hold time constraint and make some small modification to the algorithm. So, the modification look like this. Here the earliest actual arrival time must be determined, not the latest. Normally, when you look at the setup constraints, we look at the latest arrival times, but for hold constraints, we look at the shortest paths, the earliest arrival times. So, with respect to this, we will have to satisfy that the actual arrival time in the early mode must be greater than or equal to the required arrival time. Here it is greater than or equal to, right. So, you will have to satisfy this, because for hold time constraints AAT can never be less than this. So, slack you can calculate similarly, and you can adapt the ZSA algorithm to handle this, but the thing is that here you may not be able to set all these slacks to exactly 0, because that might force some TV and TE value to become negative in that case in early mode analysis. So, this is one constraint here, that is why it is sometimes called neared 0 slack algorithm, not exactly 0 slack. Okay. So, to summarize, we can have early mode or latest mode, both kind of 0 slack analysis. So, if it does not satisfy early mode budget, the delay constant can be satisfied by adding some delays. but if you add some delay, then some late mode constraint might get violated. So, what is normally done is that you first consider late mode analysis and design the circuit that way, and subsequently you use early mode analysis just to confirm that the early mode constraints are satisfied, because normally hold time constraints are not as serious as the setup time constraints. So, first you do the late mode analysis, then you see which of the early mode constraints are getting violated still, and try to tune the circuit netlist and trying to address them. So, I think with this we come to the end of this lecture. Thank you.